So in this video, we're going to do a simple proof. We're going to show that when we have an equilateral triangle and we draw an altitude of the equilateral triangle, that it will create two congruent triangles. So we'll start by drawing an altitude. By definition, an altitude must go from a vertex to the side opposite and form a right angle. Now that we've drawn in this altitude, we will label the other side having a point D, and we'll say that BD is an altitude of triangle ABC. Now we see that by definition an altitude must go from a vertex to the side opposite and form a right angle. We have that, but now we can conclude that the angle on the opposite side must also be a right angle because we started with a straight segment AC, and together this is also a straight angle. So these two angles are a linear pair, and if one is 90, then the other must be 90. So now that we know that those two angles are congruent, and we have a pair of congruent sides, we have two of the three parts of the triangle, and we can also say this is a shared side of the triangle. We can use the reflexive property to show that BD is congruent to itself. So we have three parts, and because this is an angle side-side pattern, we need to use the HL theorem because these are right triangles now. So, given that triangle ABC is equilateral, we know that AB is congruent to BC by the definition of equilateral triangle. Because in an equilateral triangle, we know all sides are congruent. We can also say that BD is congruent to itself by the reflexive property of congruence. And we know that angle BDC is a right angle because BD is an altitude of triangle ABC. And we know that angle BDA is also a right angle because it forms a linear pair with angle BDC. This means that triangle ABD is congruent to triangle CBD by the HL theorem, which stands for hypotenuse leg theorem. Now that we know the altitude creates two congruent triangles, that means that we can show that the altitude BD is not only an altitude of the triangle, but that it must also be a median of the triangle, and it must also be an angle bisector of the triangle. So the altitude of an equilateral triangle is also a median and is also an angle bisector. Because these two triangles are congruent, their corresponding parts must be congruent. So I can mark that angle CBD is congruent to angle ABD. I can mark that angle CBD is congruent to angle ABD because CPCTC, that is the acronym which stands for corresponding parts of congruent triangles are congruent. Once you show two triangles are congruent, then all of their parts must be congruent. Further, we can say that segment AD is congruent to segment CD. Again, I can say this by CP/CTC, corresponding parts of congruent triangles are congruent. Well, I'm showing you this because if a segment goes from a vertex to the midpoint of the opposite side, and we see it's the midpoint because these two segments are congruent, that would make BD a median. I can show that since segment BD creates two congruent angles here, that makes BD an angle bisector. So the altitude in an equilateral triangle is also a median and is also an angle bisector. Finally, we can now say that, well, half of this triangle forms a 30, 60, 90 special right triangle. We can say that because we know that in an equilateral triangle, all three angles are 60 degrees. But since we just showed that the altitude is also an angle bisector, that means that each of these angles here are 30 degrees. And because the altitude forms a right angle, we have a 30, 60, 90 right triangle. And in our notes for 30, 60, 90 right triangles, we said that whatever the length of the hypotenuse is, then the side opposite the 30-degree angle is the short side, and that is half the hypotenuse. And the side opposite the 60-degree angle is the median side, and that is square root of 3 times whatever the short side is. So to give an example of this, if I have a hypotenuse that is 4, I would divide that by 2 to get the short side, and I would multiply that by radical 3 to get the median side. And this works only for a 30, 60, 90 triangle. That's why we call it a special right triangle. So there are a bunch of things we just discussed with equilateral triangles and the altitude of an equilateral triangle, and how we can identify it as a median, an angle bisector. It constructs 30, 60, 90 triangles. It constructs two congruent triangles. And these are things we've done through the year. I just wanted to package it all together because we will be using this skill set to solve more complex problems in geometry.